Hi, Physics 100. This is the second video for Chapter 7, which is nuclear energy. Sorry we got cut off in the last one, but it probably was the correct length. It was about 40 minutes, so that's enough. So you can take a break, and now we're back. So I'm going to show you the boiling water reactor and the pressurized water reactor. Again, boiling water reactor, most common in the United States, and also simplest, right? Very simple to understand. So here's the nuclear pile or the nuclear core. So we have our nuclear material inside here, which contains the uranium-235, which is fissionable. We have our control rods in there, and it's sitting in a containment vessel, which is made out of lead, that will not allow any of the neutrons to escape out into the environment because they're dangerous they cause cancer. So we want to make sure that the neutrons from this have to stay inside of this chamber, okay? So that's the first thing. That's really important, okay? So this is called a containment vessel. They usually have this kind of dome top. It's not filled all the way up. It's purposefully filled 3/4 of the way up. So that means that there is steam in here, no air, okay? So this would be water vapor in this top layer here and water liquid down at the bottom. Okay, so here's what happens. The uranium-235 naturally give off neutrons. So one uranium-235 hits another one, hits another one, hits another one, and I get the chain reaction going. That creates heat and other neutrons. Those neutrons hit another uranium-235, another reaction, more heat. So over time, this water starts to heat up, right? That's why I have to keep pumping it. So I pump it in at a certain rate. As it moves up to here, as it passes the core, it heats up because it's interacting with those really hot core, right? And so the water temperature here should be higher up at the top than it is at the bottom. So it's boiling at the top. So the steam comes off. Now, not only is this water, the water is not at 100 degrees, it's at a very high pressure. So look at the pressure, it's at 1,000 PSI. So 15 PSI is what we usually feel. So I'm going to tell you what that is in atmospheres. 1,000 divided by 15, that comes out to 67 atmospheres. So the pressure inside of here is 67 times higher. The pressure of this steam is 67 times higher than normal air pressure that we're used to. So that means it doesn't boil until you get to 540 degrees Fahrenheit instead of 212 degrees Fahrenheit. But again, it's boiling. And that steam comes off. It's at high pressure. It's going to push past this turbine, turn the turbine. That turbine is connected to an axis, and that axis is going to turn magnets and wires and generate electricity like we learned in the last chapter. So traditional turbine, okay? After that high temperature, high pressure water goes past the turbine, you want to condense it so that this side is always at a lower pressure than this side. So what better way to get the pressure down but to liquefy the water? And the way you liquefy the water is you put it in a heat exchanger, which is a pipe that has our reactor water going through it. And on the outside, it's interacting with cold water that's coming in this way and going out that way. Now, this is a simplified diagram. There's no nuclear reactor in the United States who this water would just come from a lake and go back out to a lake. Usually we put it through a cooling tower, and there's a couple of other steps to make sure that no polluted water, no water that has any kind of toxins in it from the nuclear reactor, that's any kind of leaking, makes it into our water streams, okay? So this is a super simplified version. Okay, now the water is condensed back down to a liquid. Again, it's going to still be at high temperatures compared to what we're used to, but it's below 540 degrees Fahrenheit, and I pump it back into here. It goes around again, okay? So the only thing different from what we already learned about traditional power plants and this one is this part, right? Everything else over here, I could have put a coal-fired power plant and drew the picture for it. It would be the same. I could put a natural gas-fired power plant and it would be the same. Good. It's just how we're creating the heat. So that's the simplified version. It's called a boiling water reactor, BWR. I boil the water in one step, make the electricity with that boiled water. Okay, here's the other kind. A little fancier. Okay, same idea. I have my outside containment vessel and I have my inside containment vessel. Still pumping the water. The water passes the nuclear core, goes up to very high temperature. On this side, it's at a pressure of 2,200 psi. Okay. On the other side, and 600 degrees Fahrenheit, goes through this heat exchanger. The water from the reactor is in the pipe on the inside and gets pumped around. The water on the outside of the heat exchanger carries away, this is cold water now, colder water, carries away much of the heat from that pipe. Generates boiling water right here inside this steam generator, right? So this incredibly hot water inside the pipes is going to boil the water on the outside of the pipes in the heat exchanger. So it's not the primary water from in the reactor that turns the turbine, but a secondary water that makes the steam. And then the rest of the way, the process is the same, right? High pressure steam turns the turbine. The turbine is mechanically connected to a generator. That generator turns a series of magnets and wires and generates an alternating current that goes out into the electric grid. Down here, that this steam has to be condensed back into water. Otherwise, you won't have that pressure gradient. You won't have this side much higher in pressure than this side if you don't condense it right after the turbine. So you have a second heat exchanger. Okay, here comes the cold water, gets pumped in. Cold water interacts with this water here, condenses it from steam back into liquid water. That guy gets pumped around into that cycle. This cold water that's coming in here goes on the outside of those pipes, gets heated up, and carries that water into a cooling tower or a lake. Again, no nuclear reactors in the United States right now would go directly into a body of water. There would be a cooling tower first, and then maybe secondary or tertiary water would go back into a lake. We also are very critical. There's a Barnegat Bay nuclear reactor on the Jersey Shore, that this hot water is only a few degrees. It has to be less than 5 degrees warmer than when it went in, because we don't want to create algae blooms and other kinds of bad biological things happening down on the Jersey Shore or wherever we're dumping this water. Okay, so that's called thermal pollution. So we have to be very careful. They're not allowed to drop water in that's 20 degrees warmer. Okay, it's a very subtle difference between this pipe and this pipe. So we got to pull in a lot of water to do that then, if it's only a subtle difference. Okay, what's this one called? This is called a PWR. 2 steps, 2 heat exchangers, 2 pumps, right? Primary water, secondary makes the steam, tertiary water cools off the steam. Okay, so you got 3 sets of water really, 2 heat exchangers. Good. Okay, next thing we're up to, not going to spend a lot of time on it, but there's 2 methods to enrich the uranium, because remember, the uranium coming out of the ground, you could not possibly do this type of reaction, okay, because it's you couldn't physically put the uranium close enough to each other to set up a chain reaction. It's not concentrated enough. So you have to take it from 0.7% up to 3%. So 2 ways you do that. You usually do that at a different facility and then bring the material to it. One is called gaseous diffusion, and the other one is called a centrifuge. So most of in the world go by a centrifuge, and the centrifuge operates by a very simple principle. if I have both U-235 and U-235, U-238, sorry, in the same space, okay? I have to make, both of these are solid, so how do I make them a gas? I put them through a chemical reaction so that they chemically react with fluorine. And that makes this guy a gas and this guy a gas, okay? Those uranium with fluorine are gaseous at room temperatures, okay? Or at whatever temperatures they have in the reactor. Now I have both of these things and I put it in a centrifuge. This one is much, well, not much heavier, but a little bit heavier than this one. So I zip them around the outside. What happens to I zip them around in a centrifuge. What happens to the U-238? Since it's heavier, it's more, it's going to be pushed to the outside to a larger degree. And I can separate off it from here, and the 235 is more likely to go here. And then I do this separation over and over again. So maybe after just one centrifuge, I only increase the amount on the outside from 0.7 to 0.8%. Then I have to do it again to get it to 0.9, then I do it again. So they do this over and over and over again, hundreds of times, just to get it from 0.7 up to 3. So a lot of work has to go on inside of these centrifuges, okay? If you want to make bombs, you have to put it through, you got to get to 90%, so it may have to go through thousands of centrifuges. So whenever we're worried about rogue states like North Korea having nuclear energy, one of the things we're checking for is, do they have facilities where they're hiding centrifuges, right? So these centrifuges, and I can show you a picture, that's where the enrichment goes on. And we want to make sure that they only have centrifuge capacity that can go from 0.7% up to 3%, right? We're not denying other countries, right? We're not supposed to be, the United States is not supposed to be the big brother of the world. We're not denying other countries the ability to have nuclear power to make electricity for their citizens. That's a good thing, right? What we are trying to deny them, it's interesting that one country has the ability to do that, is the ability to make nuclear power, to make nuclear bombs. There's about 4 or 5 countries in the world that have the ability to make nuclear bombs, and we don't want that club to be any bigger than it already is, okay? So there is another way, though, another way in order to enrich the uranium, and that is to use a nuclear reactor not just to create energy, but to also make nuclear material. And those kinds of reactors are called breeder reactors. And I'm going to show you the chemical of the nuclear reaction that occurs. So there are breeder reactions in France, Russia, Japan. They produce enough fuel for its own operation, which means to generate electricity, and they also generate additional fissionable fuel for other reactors. So they're basically a factory and a power plant and an electric power plant at the same time. Okay, how would that work? Well, here's how it works. You take the U-238, which is not fissionable, okay, and you hit it with a fast neutron. Okay, so don't slow it down. Don't have the light water reactor. Okay, you have to have a different kind of material that keeps the neutrons fast. Instead of going to U-235 breaking up into fissionable material, that neutron makes U-239, which is unstable, only lasts a fraction of a second, undergoes something called beta decay to make Neptunium-239, another beta decay to make Plutonium-239, which is atomic number 94. So you don't have to worry about this idea. But notice 2 things about it. First of all, Plutonium-94, which is always 94, Plutonium-239 is fissionable. You can take it, put it in a different place with slow neutrons, and it can undergo the same reaction as uranium, a similar reaction to uranium-235. So you're making plutonium out of naturally occurring uranium. Remember, this is the majority of the uranium you find in the earth. But notice something else. This is not a chain reaction. A neutron goes in, I don't have neutrons coming out, so that's a good thing. In those breeder reactors, they give off heat, but you have to keep supplying the neutrons from someplace, okay? They are not a self-sustained chain reaction, which is good because they could easily go out of control. We have never done this in the United States. We considered it at one point early on, but just this idea of being able to make plutonium kind of scared us, and it's a very good scare, okay? So the United States has not done this, okay? I think even in France, they're not doing it to the same degree that they once were. I'm not sure about Japan. Most of the breeder reactors are in Russia. Okay, just 2 more pages of notes. The biggest issue with nuclear power is, well, first of all, accidents, right? And also what to do with the waste that come off of it. All those fission fragments, although they can't undergo more fission and you can't really use them to generate heat, they are all radioactive. If people come into contact with them, the likelihood of those individuals getting cancer is very, very high. So these low-grade nuclear wastes that are inside the reactor, once a year when they change the fuel rods, they have to remove that material. Okay, remember, the reactor is closed up. The only thing going around in a circle is the water, right? So all of this, I hate to say it, but all of this crap at the end, you've got to take it out and you have to store it someplace or put it someplace away from human beings and animals and water supplies and the air and the soil, so that we don't get sick from it, right? We don't cause cancer clusters from this nuclear core, okay? Although it's done reacting to generate electricity, the products are still things that are radioactive themselves, okay? It would be great if they decayed into stuff that was harmless, but they don't. They decay into other materials that take thousands of years to make it all the way down to harmless stuff, okay? And we'll see that in a second. So here's some ideas about where to put the waste, right? Because they're radioactive. That low-grade waste is radioactive for millions of years. One is, can you put them in salt mines, okay? Because salt mines are very dry, so after you pull the salt out, you put the nuclear material in there, and then over time, the salt, over thousands of years, the salt is kind of fluid a little bit. The pressure of the salt will contract around the nuclear waste and sort of confine it forever. That's one place. Another idea is to put it in seabed sediments, which doesn't sound very good to me, right? The last place I want to put it in is the ocean. The ocean has water, and we could wind up with ocean water that is radioactive. Put it in deep in the earth, inside of rock. Some people talked about putting it into polar ice caps. These two scare me, right? Because ice caps can melt, okay? Ice is not stable enough for me to put this nuclear waste. I like the idea of salt beds, or deep within the dry sections of the earth, away from cities, places like Nevada. Bury them deep inside those kinds of deserts, right? Okay, so that's a big issue. I'm going to show you a couple more things from your textbook related to that. But we want to spend just a few minutes now talking about 3 accidents that happened in the world, about 30 years apart for each one. Actually, the first 2 were close together, and then the last one was much further apart, which is a good thing. Okay, so very different outcomes for the 3. Okay, so the first one that we're going to talk about is really the only nuclear accident that we've had in the United States at a power plant. Okay, there may have been other things that happened at military bases where things have gotten polluted, and we know that for sure. Actually, there's a couple of military bases that we're very worried about because they were doing nuclear research, but there was no power plant there. So the one power plant is called the 3 Mile Island Power Plant. Okay, and this accident occurred in 1979, and if you remember, if you've seen anything, obviously you guys don't remember, it's way before your time, but at the time Jimmy Carter was president. Okay, it's in Harrisburg, Pennsylvania. Okay, and the type of accident it is called a LOCA, or a LOCA accident, and that means loss of coolant accident. Okay, so That's going to be the case in all three of the ones that we have. So what happened is there was a pump failure, and then there was multiple pump failures. So the first pump broke, and then the replacement pump that's supposed to kick on also broke. So what you had was you had this nuclear reactor occurring, okay, and nobody pushed the control rods in immediately. And so if you can't pump the water around, you can't pump the water around in a circle, you're going to have a buildup of heat inside of here, and it's going to melt some of the components like the gauges and the valves, and maybe this pump broke, and there's no way to carry the heat out. So what happened was some of the coolant here, not the primary coolant, but some of the coolant was lost to the outside. So a little bit of nuclear material was lost as steam that came off of the power plant, right? And at the time, there were no acute deaths. An acute death is a death that occurs right away directly because of it. So nobody got burned or nobody died of cancer instantly. And then there's one additional death in the area due to cancer, and that's an estimate. So if you think about how many people are dying from the coronavirus, in New York City, we're losing 600 people a day. We made such a giant thing about the 3 Mile Island accident when actually probably there's just going to be one additional death to cancer in the Harrisburg area over the next 50 years. So people probably have been monitoring that because now a lot of time has passed since 1979, right? Just basically 40 years ago. There's no cancer cluster or anything like that, right? The probability of that amount of small amount of nuclear radiation that went up into the atmosphere that day, of somehow it causing it, the estimates are one extra death in that area. So again, that though signaled basically the end to creating new nuclear power plants in the United States. It scared the citizens of the United States. It created a movement called the No Nukes movement in the early 1980s, and no additional nuclear power plants were created after that. The only thing we've been doing is continuing to run the ones that were already up and running, and they're slowly coming offline as they come to the end of their lifetime, right? There's one on the shores of the Hudson River in upstate New York, very close to here, that's about to close in the next couple of years. Okay. Second accident that we're going to cover is the worst nuclear power plant accident that's ever happened in the world. It happened in 1987 in southwest, what was then the Soviet Union, the USSR, and is now part of the country of the Ukraine. It was always the Ukraine, but the Ukraine was associated with the Soviet Union in those days. Now, the Ukraine, as you know, is a completely separate country that's actually enemies with Russia. There were 31 immediate fatalities because of this accident. And those people were the people who worked directly at the power plant. They were doing a cleanup at the time, right? They were switching something out. The reactor was supposed to be down, and during this restocking of the fuel and cleaning out the old materials, something went terribly wrong, and the reactor went critical. So the 31 immediate deaths, you could call those are the acute deaths. Another 4,000 people over the next 50 years or so will die of cancer related due to the release. And those 4,000 people are not confined to the Ukraine. The way the weather pattern was that day when the coolant loss and that steam went up into the atmosphere, the weather carried it to Western Europe, and there were cancer clusters in different places where it rained, and the precipitation actually had nuclear material in it. Okay, so 4,000 deaths expected. 6,000 cases of children with thyroid cancer due to drinking milk with radioactive iodine-131, which is one of the byproducts of the nuclear reactor that went off into the steam. Okay? There were 10 times the amount of radiation released during the Chernobyl accident than was released when we exploded the bomb over Hiroshima. So in an actual nuclear bomb had less radiation, because that was in the 1940s when the bombs were smaller, okay, than the Chernobyl release, which is amazing. Okay, and the third accident that we're going to quickly talk about is the most recent one. It happened in 2011 in Japan, Fukushima Daiichi, I think I'm pronouncing that right, Daiichi, and it resulted from an earthquake and a tsunami that happened. So no human error that occurred at all, right? Maybe a little bit of a design error that this nuclear reactor was put close to. So the nuclear reactor was put close to the seashore, and then the tsunami actually engulfed the nuclear reactor, and the salt water from the tsunami rusted out many of the pumps. And it was the same kind of accident like 3 Mile Island. It was a loss of coolant accident. So it had only 10% of the radiation release compared to Chernobyl. Okay. And that is all of the notes that I have from that from chapter 7. I just want to go back and see if there's anything from the textbook that I want you to review. Okay, you definitely want to spend some time with the 2 different kinds of nuclear reactors, right? This is the pressurized water reactor, and then back a couple of pages was the simpler boiling water reactor. Okay, I'm gonna just grab your book, which I have down here because there's a couple of cool things. All right, we definitely really like this idea, right? That the way to get energy was fission of larger nuclei or fusion of smaller ones, and fusion we've not been able to harness yet. Okay, some of the most important research that occurs on the fusion front occurs at the Plasma Physics Laboratory that's associated with Princeton University. And they've been trying probably for the last 30 years to get to a point where they call break even. And break even is the amount of energy that they put into the fusion process is equal to the amount that's released. And they still haven't been able to get to that break even point. Again, it's very hard to figure out the engineering. This reaction requires a huge amount of energy. You have to get to such high temperatures that what do you hold the reactor materials in, or any kind of metal or any kind of physical material would melt, and the stuff would just escape, and you'd lose all of that heat. Okay, so you actually have to do it in something called magnetic confinement, and there's a special type of device called a tokamak reactor. Here's a nice one in yours, a simplified version of a fission reactor here, but I just want to show you what the tokamak looks like. Okay, so we would do fusion. One mechanism is by magnetic confinement. Okay, again, long way away. You guys might see it in your lifetime, but I'm probably going to be dead before we have practical nuclear fusion. Okay, it would be fantastic if we did, but okay, here's a fusion reaction here. Yeah, right. So you take these 2 heavy hydrogen and another heavy hydrogen. They're both hydrogen because they have 1 proton. This one's called deuterium because it's got an atomic number of 2. This one's called tritium because it has an atomic number of 3. You put them, smash them together, make this very stable nucleus of helium, right? Not radioactive at all. Nothing, none of the byproducts here are radioactive. Kicks out a neutron. Also kicks out a ton of heat. Here's the tokamak. So basically what you do is, it looks like a donut, and it's a space, in which there's huge magnetic fields. Just look at all these coils going around the outside, and those huge magnetic fields confine the material that's going to react, and that's at very high temperature, so it's never touching any of the walls, right? Can't touch anything because it's so hot. So it's called magnetic confinement, okay? So we're a long way. How would you interact and pull that heat out of here? They're not even up to the point of designing the reactor and how the heat exchange would go on. They're just working on the fact of trying to get this thing to react in the first place, okay? So again, long way away. Here's another version of what you would do. This is called Possible Design for a Deuterium-Tritium Fusion Power Plant. And here, actually, same design. Here's the tokamak here, okay? So you would confine the plasma in here. There would be a vacuum going around, and then you would do the heat exchange with liquid lithium, which is at a much higher temperature, and have the power plant here. But again, we're a long way away from that. Okay, one more thing I want to show you real quickly. You can maybe take a picture of this. Okay, this table is going to be in your notes for the chapter that the textbook publisher puts out. But again, these are some of the options for storing the waste that comes out of a fission power plant. So some options for nuclear waste disposal. Dry casting, shallow burial, which is less than 1 kilometer, subsea bed burial, deep hole burial. This is 10 kilometers, so we'd have to make a hole that's 6 miles into the earth and pump the nuclear waste into that well below the ground, okay? That requires a lot of energy to do that. So I hope we're going to make so much more energy to make this worthwhile if you're going to go to that extent. Here's a crazy one, right? Put it into outer space. Well, good luck with that, because you need to launch a rocket, and what happens if that rocket crashes? The rocket would crash with all of that nuclear material and spew all over the ocean, or maybe worse. We talked about this a little bit, is deep ice sheet disposal. And last thing was dedicate islands out very far away from anybody, and bury it in remote islands to keep the way away from population centers. But that's not really fair to, we'd have to evacuate all the people off of those islands. And again, who's to say that somehow it doesn't seep into the ocean? Okay, so again, these are advantages, disadvantages, different possibilities. And last one, this is probably the best one, right, is to actually let them undergo another nuclear reaction. Again, hopefully we don't use more energy to do this, so that we change those radioactive nuclei into shorter-lived nuclei. So instead of the nuclear waste lasting for 10,000 years, it would last a much shorter period of time, like 100 years or 10 years, and then the radioactive waste would be safe at the end. So you'd have to react it more, and that's going to take energy. So the whole idea is to create energy, not to use up energy getting rid of the waste. Okay. All right, that's it for this video and all of the notes for Chapter 7.